closely at a piece of raw, unrefined gold ore. Before any extraction begins, the target element is locked tight within an incredibly dense, rigid physical matrix of waste rock. The primary metallurgical challenge is one of extreme disproportion, isolating mere grams of this specific target element from thousands of tons of barren earth. To solve this massive scaling bottleneck, the mining industry relies on a high-volume cyanation process known as Counter Current Decantation, or CCD. Rather than relying purely on mechanical sorting, CCD operates by forcing the gold through a strict sequence of chemical phase transformations. This diagram illustrates the macroscopic pathway of the entire operation. It tracks the gold as it transitions from a solid state within the raw ore into a dissolved liquid solution, and finally back into a purified solid ingot. We can break this pathway down into 3 operative stages: leaching, washing, and displacement precipitation. CCD is effectively a deliberate chemical architecture engineered specifically to manipulate elemental phase states to achieve absolute physical isolation. The process begins after the raw ore has been mechanically crushed and fed into the primary solvent tanks. This initiates the leaching phase. The goal here is to break the physical bonds of the solid matrix and force the trace gold out into an aqueous state. To achieve this, the tanks are flooded with an oxygenated cyanide solution, typically sodium cyanide or potassium cyanide, which acts as the primary lixiviant. However, this chemical environment is highly unstable. If the pH level drops, the cyanide rapidly degrades. To prevent this degradation, operators add lime to the mixture. The lime functions strictly as a protection alkali, chemically stabilizing the pH of the solution. This shows the molecular mechanics inside the stabilized tank. Oxygen and sodium cyanide molecules actively attack the solid lattice of gold atoms, stripping them away into the surrounding fluid. This interaction creates a specific, highly soluble aqueous complex, the gold dicyanoaurate ion. Through this reaction, the target metal is successfully detached from the physical ore. The gold is now entirely in a liquid phase. But zooming back out to the macroscopic scale, the resulting product inside the tank is not a clean liquid. It is a thick, dense slurry. This slurry is a chaotic mixture where the newly formed gold-bearing liquid remains trapped alongside thousands of tons of barren solid waste, or tailings. While the leaching stage succeeds at chemical separation, it creates a severe physical separation bottleneck that requires an immediate mechanical solution. That solution is the washing stage. Its strict operational goal is to physically pull the pregnant aqueous solution away from the barren solid tailings. Processing this slurry continuously requires massive industrial architecture. Look at these interconnected circular thickening tanks and conveying systems. The primary mechanical setup driving this separation is typically a 3 to 5 stage dense filtration system, or a counter current decantation circuit. Inside this circuit, clean water or gold-depleted lean liquid is forced against the filtered slurry. This active washing pushes the pregnant gold solution forward through the system. Pumping clean water into the wash provides a secondary chemical advantage. It actively dilutes the concentration of sodium cyanide left trapped inside the solid waste. To maximize operational efficiency, all of the resulting gold-depleted lean liquid is continuously cycled back into the primary leaching tanks. Maintaining this closed loop significantly lowers the overall loss of cyanide and simplifies downstream sewage treatment. By the end of the washing circuit, the flow diverges. The discarded tailings are moved out of the plant, while the pregnant gold solution flows onward. At this exact point in the process, the gold exists in its most purified and isolated liquid state. The washing bridge converts the isolated chemical reaction of the leaching tanks into a sustainable, closed-loop industrial flow. With the liquid isolated, the plant shifts to its final chemical objective, forcing the dissolved gold out of the aqueous phase and back into a solid, collectible state. Before this precipitation can occur, the pregnant solution must be rigorously purified and completely deoxidized. Operators then introduce the chemical agent responsible for driving the phase change, metallic zinc powder. This diagram displays the core stoichiometric equation for the displacement reaction. On the reactant side, metallic zinc powder is injected directly into the alkaline cyanide solution alongside the dissolved gold complex. This triggers a redox mechanism. The zinc acts as a strong reducing agent, bonding directly with the cyanide to form a new zinc-cyanide complex. As a consequence, the gold atoms are forcefully displaced from their previous bonds. Because of its specific kinetic properties, this reaction is exceptionally rapid and ensures nearly complete metal replacement within the liquid. Inside the precipitation tanks, microscopic gold particles fall out of the aqueous solution, raining down to collect as a dense solid at the bottom. Zinc displacement elegantly exploits precise redox potentials to execute a highly selective, instantaneous liquid-to-solid extraction. The immediate physical output of the zinc displacement stage is a raw, unrefined material known in the industry as gold mud. This mud contains a gold concentration of only about 30%, heavily contaminated with residual unreacted zinc and other base metals. To strip away those base metals, operators utilize an intermediate purification step called pickling, which applies an aggressive acid wash to the mud. This prepares the material for the ultimate metallurgical upgrade, separating the pure metal from the final impurities via high-temperature flux smelting. This upgrade takes place within the smelting furnace, where the material is subjected to the high temperatures required to separate metal from slag. Heat alone is insufficient. Separation at 1,000 to 1,100 degrees Celsius over 3 hours requires a precise flux ratio. The recipe demands 30 to 40% borax, 25% nitrate, 15 to 20% quartz sand, completed with 5 to 10% fluorite, soda, and manganese oxide. Once the molten mixture separates, the waste slag is discarded, leaving behind a dense, solid gold ingot. This final product completes the entire architectural journey of counter current decantation. By utilizing cyanide to force a liquid state, zinc to force a return to a solid state, and targeted fluxes to finalize the separation, the process yields a gold ingot of over 95% purity.